Good morning, everyone. Thank you for joining us today. In our last deep dive, we really laid the groundwork covering securing the continuum, the zero trust mandate. So we've established this critical foundation of security for our entire modern computing architecture. We've built this massive, interconnected system that stretches all the way from the cloud to the edge. And now we get to ask the really exciting question, what do we do with it? Well, the answer, pretty much across the board, is to power the most transformative technology of our time, artificial intelligence.
And that brings us right to the heart of the challenge we're tackling today. See, data isn't just sitting in neat centralized databases anymore. It's being generated, well, everywhere. On factory floors, across city streets, inside self-driving cars, and yeah, right on the smartphone that's probably in your pocket. This whole computing continuum we've built exists to power AI, and today, we're going to break down exactly how we make that intelligence work seamlessly across this entire distributed landscape. So let's dive in and explore how we bring intelligence to life, from the huge data centers in the cloud, right down to the tiniest sensors at the very edge.
All right, so here's our game plan. We're going to start with how AI even got so accessible in the first place. Then we'll get into the weeds of the dominant architectural pattern that powers most of the AI you see today. We'll make it real with a deep dive into Tesla's Autopilot system, and then we'll pivot to look at a super important privacy-first alternative called federated learning. And finally, we'll talk about the operational backbone that makes it all work at scale, a discipline we call MLOps, before we wrap everything up with the key takeaways. First up, AI's new accessibility. Before we can even talk about distributing intelligence, we have to understand how it broke out of the ivory towers of tech giants and elite research labs. How did this incredibly complex technology become a tool that almost any developer or company can start using? This is really the story of the great democratization of intelligence.
The real engine behind this whole shift is something called AI as a service, or AIaaS. You have to remember, for years, building any meaningful AI required this perfect storm of resources. You needed massive, unique data sets, a whole team of PhD data scientists, and your own supercomputers. It was just way too expensive for almost anyone. AIaaS completely flipped the script. Just like the cloud made computing power a utility you could just turn on, it did the exact same thing for artificial intelligence. Now these incredibly advanced capabilities are available as simple, pay-as-you-go services, a lot of the time accessible with just a single API call. That completely removes the huge upfront investment and really opens the door for anyone to innovate.
What's so brilliant about this is that it's not a one-size-fits-all model. It's a whole spectrum of access. At the most accessible end, you've got pre-trained APIs. This means a developer who knows nothing about machine learning can add super sophisticated vision or speech analysis, think Google Cloud Vision, into their app with just a handful of code. In the middle, you have AutoML platforms. This is for teams that have their own unique data, but maybe not a dedicated data science department. You just upload your data, and the platform figures out the best model for you. And then, for the experts, you have the full-blown ML platforms like Amazon SageMaker, a completely managed environment for the whole ML lifecycle. There's an entry point for literally every skill level.
Okay, so now we have all this accessible intelligence. How do we actually apply it in a world where data is being born everywhere, every second? This brings us to the core architectural blueprint for distributed AI. It's the dominant pattern, the one you're going to see over and over. And the idea is actually beautifully simple. You train your AI model in the cloud, and then you deploy it to the edge. Let's really break down what that means and why separating things this way is so incredibly powerful. The best way to think about this is the university versus workplace analogy. It just perfectly captures how these two domains work together. You see, training a modern AI model is a computationally brutal task. It's like sending the model to university for a PhD. You need massive data sets. We're talking petabytes of information, which because of data gravity tend to live in the cloud anyway. And you need a supercomputer, sometimes with thousands of specialized GPUs running 24/7 for weeks. The cloud lets you essentially rent that supercomputer on demand. It turns a massive capital expense into a manageable operational one. So yeah, the cloud is without a doubt the perfect university for training AI models.
But here's the catch. The model that graduates from the cloud university is, well, a genius, but it's also a massive, complex behemoth. It's incredibly accurate, sure, but it's also slow and power-hungry, way too big to run on a smart camera or a sensor in a car. So before it can get a job in the workplace, it needs to get specialized. This happens through optimization techniques like quantization and pruning. Quantization is basically reducing the numerical precision. Think of it like turning a giant high-resolution photo into a much smaller but still perfectly clear JPEG. And pruning is where you go in and snip away all the redundant connections in the neural network. The whole process is kind of like taking a dense 500-page academic paper and editing it down to a crisp 2-page summary that gets all the key points across efficiently.
So once that model is optimized and lean, it gets deployed out to the edge, where it finally begins its working life. This is where inference happens. Inference is the moment of truth. It's when the model takes all of its education and applies it to the real world. It takes in new, live data from a camera, a microphone, you name it, and makes a prediction or a decision right there in real time. This is exactly why we call the edge the workplace. This is where the model stops learning and starts doing. It's the payoff for all that hard work back at the cloud university.
So you might be wondering, why go to all this trouble? Why not just send all the live data back to the big, powerful cloud to make every decision? Well, there are 4 absolutely critical reasons. First, low latency. A self-driving car that spots a pedestrian can't wait for a round trip to a data center. It needs to make a decision in milliseconds. Second, bandwidth and cost. Imagine trying to stream raw 4K video from thousands of factory cameras to the cloud 24/7. The cost would be astronomical. It's way cheaper to process the video locally and just send an alert if something's wrong. You're sending the insight, not the raw data. Third, disconnected operation. An industrial controller on an oil rig has to keep working even if its satellite internet connection goes down. And finally, privacy. By processing sensitive data, like a facial scan for entry, right on the device, that raw information never has to leave the building.
Now, theory is one thing, but let's see how this all comes together in the real world. And honestly, there is probably no better example of this entire train in the cloud deployed to the edge workflow than the Tesla Autopilot system. It's a perfect illustration of this dominant pattern being executed at a massive global scale.
Let's just walk through the life cycle. It all starts at the edge with data collection. Every Tesla on the road is part of this massive data gathering fleet, collecting millions of miles of real-world driving data every single day. That data then gets uploaded to the cloud, where Tesla's engineers feed it into their powerful supercomputing clusters to train those huge neural networks. Next up, optimization. Those giant, super accurate models are put on a diet. They're quantized and pruned to become small and efficient enough to actually run inside a car. Then, those smaller models are deployed back to the edge, pushed out to the entire fleet through over-the-air software updates. And finally, we're right back at the edge for inference. The real-time driving decisions, spotting lanes, other cars, traffic lights, all of that happens right there, on the car's own specialized computer. It's the entire pattern, in one perfect, continuous loop.
Now, that train and deploy pattern is incredibly powerful, but it's built on one key assumption, that you can actually centralize all of your training data in the cloud. But what happens when you can't? What if the data is just too sensitive to ever leave a user's device? Think about your private text messages or medical records from a bunch of different hospitals. For those kinds of scenarios, we need a fundamentally different playbook. We need federated learning.
The mental shift here is actually pretty profound. The standard pattern we just talked about is all about bringing the data to the model in one central place. Federated learning completely flips that on its head. The new paradigm is bring the model to the data, wherever it happens to live out on the edge. It's a really elegant solution that lets you train a model collaboratively without ever having to centralize or compromise all that sensitive raw data.
So how does this actually work? Well, first, a central server starts with a generic, untrained model, and it sends a copy out to thousands, maybe millions of edge devices, like our smartphones. Second, each phone individually trains its local copy of the model using only the data on that specific device, like, for example, your personal typing history. Now, this is the crucial part. That sensitive data never, ever leaves your phone. Third, instead of sending the data back, each phone just sends a small, anonymous summary of the changes it made to the model, basically the mathematical learnings. Finally, the central server takes all these little updates from all the different devices and aggregates them together to create a new, smarter global model. Then it sends that improved model back out, and the whole cycle starts over, getting smarter and smarter each time.
And you've probably seen the most prominent real-world example of this without even realizing it, Google's Gboard keyboard on Android phones. Google is constantly improving its predictive text and autocorrect by learning from the typing patterns of millions of users. But they never have to upload the actual content of your messages to their servers. They get to build a powerful, globally effective model while totally preserving the privacy of every single user. It's a truly remarkable application of this technique.
So, we've talked about how to build and deploy these models, using either the standard approach or the federated one. But here's the thing, building the model is really just the beginning. An AI model isn't like a normal piece of software you build once and then forget about. It lives and operates in a dynamic, constantly changing world. And that brings us to the final, absolutely critical piece of the puzzle,
the operational backbone that makes all of this robust, scalable, and reliable when it's out in the real world.
The core problem that we're trying to solve here is something called model drift. It's this natural degradation of a model's performance over time, simply because the real world changes. The data it starts to see in production begins to look different from the historical data it was trained on. So imagine a model that was trained to predict customer demand. It's going to start failing if a new competitor suddenly enters the market and completely changes how customers behave. Model drift is inevitable, and if you don't actively manage it, your smart systems will slowly become dumber, or even worse, they'll start making dangerously wrong decisions.
The solution to model drift is MLOps, which stands for Machine Learning Operations. MLOps is really the discipline of taking all those battle-tested principles from the world of DevOps, things like automation, continuous integration, continuous deployment, and applying them to the unique challenges of machine learning. It's all about creating automated processes to reliably build, deploy, monitor, and maintain these models once they're out in the wild. This is what turns a fragile AI science project into a robust, enterprise-grade intelligence system that can actually adapt and improve over time.
So what does this MLOps lifecycle actually look like? Well, first, you have automated training pipelines. These are workflows that can automatically pull in new data, retrain a model, test its performance, and then package it up for deployment. It removes manual error and speeds everything up. Second, continuous monitoring. Once a model is out there, MLOps tools are constantly tracking its accuracy. When the system detects drift, it can automatically trigger that retraining pipeline, which basically creates a self-healing system. And third, a model registry. Think of this as the single source of truth for all your models. Just like source code, models need to be versioned. A registry tracks every version, what data was trained on, its performance. This is absolutely critical for governance, for being able to reproduce results, and most importantly, for being able to safely roll back to a previous version if a new model starts acting up.
And that brings us to our wrap-up. We've gone all the way from the democratization of AI to the dominant train and deploy pattern to its privacy-first alternative, and finally to the operational discipline needed to make it all work. So let's just distill this down to the most important takeaways.
If there is one single thing that you take away from our time together today, let it be this. The future of AI isn't about choosing the cloud or the edge. It's about the partnership between them. The cloud is the powerful university where these massive models can learn from incredible amounts of data, and the edge is the responsive workplace where smaller, efficient versions of those models make smart decisions in the real world, in real time. This symbiotic relationship is the engine that's going to power the next wave of innovation. And that, of course, leaves us with one last thought to chew on. We're starting to figure out the basic patterns for distributing intelligence, but as this becomes truly ubiquitous, with AI running on billions of different devices, what new challenges are going to pop up? We're going to have to think really hard about how to secure this massive new attack surface, how to orchestrate updates and rollbacks across these huge fleets of devices, and how to navigate all the complex operational and ethical questions that come up when autonomous decisions are being made everywhere, all the time.
In our next deep dive, we're actually going to explore the foundational technologies that make a lot of this possible, as we cover the cloud-native toolkit, containers, Kubernetes, and serverless. Thank you so much for joining us for this explainer, and be sure to subscribe to our channel Tech, AI, and Beyond for more deep dives into the technologies shaping our world.